Okay, so in this section we are talking about optimization, and essentially we're going to use the strategies that we've had for finding local and absolute extrema, and we're going to apply these to applied problems. The problem-solving procedure that you'll use, it starts off somewhat similar to a related rates problem. So the first thing that you want to do is draw a picture if appropriate. Oops. Okay. Okay. And in most problems, it will be appropriate to draw a picture. And then you want to introduce notation. For the quantity that you're going to be asked to maximize or minimize. So each of these problems is going to ask you either to maximize or minimize some quantity, so you want to label that with a variable. And just for the purpose of stating the rest of these steps, I'm going to call that variable Q, but usually you'll choose some other variable that corresponds to the actual quantity. So usually we use A for area, V for volume, that kind of thing, so that it's clear what we're talking about. You'll also want to introduce notation for any of the other quantities. So when I say notation, that really means assign a variable. And other quantities that are varying. Oops. Okay. The third step would be to determine equations that relate the variables. And so these will often be geometric equations that we know, such as the area of a circle or the volume of a cube or something like that, or something to do with geometry that relates to the picture that you've drawn. So we'll see examples of this when we do some problems. And then the fourth step is to use the equations from step 3 that you've just found. And you want to write Q in terms of the other variables. So remember, Q is the thing that you want to maximize or minimize, and so we want to write it use the equations from step 3 to write Q as a function of one variable. And the reason we want to do this is so that we can take a derivative, right, of one variable. Because that is the first step when we try to maximize or minimize a function. So another part of this is we want to identify the domain. Okay, and then the last step is to find the absolute extrema. And so you'll just go through the steps that you already know for finding extrema. So we'll absolute or local, depending on the domain. Extrema of Q, that thing that you want to maximize or minimize on its domain. And so this is the part that involves taking the derivative of Q, right? Finding the critical points and so on. And so that part we already have a procedure for, so we're not going to list those steps here. This is really just the setup of how to do these types of problems. Okay, so let's do an example. So here we have a farmer that has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. So we're assuming that the river is completely straight. The bank is a straight line. So this is an idealized version of a real world problem, but we can approach it this way. So he does not need a fence along the river. He just wants something that creates a rectangle. So say this is our river here, a rectangular field like this, and the only parts, maybe I'll do this in a different color, that he needs fencing for is this orange part, right? So along the river, that part is not using any fencing. And then we want to maximize the area. It's asking for the largest area. Okay, so the thing that we want to maximize is the area, so we should label that with a variable. So this will be the area of the field. And then the other quantities that are going to be changing, since this is a rectangle, we know that it will have a length. So I'll label this side as the length. This is the length of the field. And then the width I'll label with a W. Oh, oops, that's the width. Width of the field, right? And those are all the quantities that are related to this particular problem. And so we have some equations that will relate these variables. First of all, we know that the area of a rectangle is equal to length times width. And then we also know that these orange sides have to add up to 2,400, right? So we know that we only have 2,400 feet of fencing. Supposedly we would want to use all of it because we want to create the largest field possible. So we would want to use as much fencing as we have, right? So we know that if we add up the length L, and then we have two sides of length W, so 2W, that should be equal to 2,400, the amount of fencing that we have. And so that means that L is equal to 2,400 minus 2W. Okay, now combining this equation here and this one here, so just substituting this expression that we now have for L in terms of W, we can get, so substituting our expression for L into this equation, A equals L times W, we get A equals L, we're replacing L with 2,400 minus 2W times W. So now we have something that is in terms of one variable. So A is equal to some expression of W. W is our independent variable. And we can simplify this or just multiply it out. And we would get this 2,400W minus 2W squared. Okay, so now we've gone through the first, let's see, 3 steps, and we determined our quantity, which is A, in terms of one variable, and we also want to identify the domain. So usually these are, the domain is going to be dictated by the physical restraints of the problem. So for example, a width, that's describing the width of a rectangle cannot be less than 0, right? So one restraint that we have on W is that it has to be greater than or equal to 0. The other thing we have, the other restraint on W is that we only have 2,400 feet of fencing. So in the worst possible case, or in the most extreme case, L would be equal to 0, and that would mean that W, well, if we just try to picture what that would mean, if L is equal to 0, then that means the fencing will go straight up and then come straight back down and not travel any width, or, well, we called this the length, but it won't travel horizontally at all. That means that if we use the entire length of fencing, it will go 1,200 feet and then turn back around and go another 1,200 feet back to the river, which means that, well, this would have 0 area, so it's definitely a bad idea for us to build a field like this, but it is a restriction. This is really the most extreme case, or the most that W could be, right? So at most, W will be equal to 1,200. But like I said, this is probably a bad idea. We want to maximize the area. So what we're going to do, this is going to be our domain, right? And we want to take the derivative now of A. Okay, so now we're working on the maximization part. So we'll take the derivative of A with respect to W, A being a function of W. So we would get 2,400 minus 4W. If we want to solve for the critical points of this, we will set this derivative equal to 0, and we would get 2,400 equals 4W, and then our solution would then be 600. That's our only critical point. Just one. And then what we have is one critical point, and we are looking to maximize A on the interval 0 to 1,200, right? So remember, if we want to find the absolute max on a closed interval, all we do is we just take our function, we evaluate it at the endpoints and also at any critical points in the interval. So since 600 does lie in between 0 and 1,200, we evaluate A at 600, and then we also evaluate at 1,200 and at 0, those being the endpoints. Okay, now if we plug in 0, remember this is our, so we're using this equation for W, or in fact, we'll use this second one where we multiplied this out. Okay, plugging in W equals 0, we would get 0 minus 0, so 0. And then also with 1,200, remember we already said that if W were equal to 1,200, then the length would be 0, therefore the area would be 0. But you can also check this by plugging in 1,200 to our formula for W. If we do that, we would get 2 times 1,200 squared, and if you throw this into a calculator, you will get 0. So now, looks like neither of those is going to be a maximum, so we just want to evaluate at 600, and that should give us our maximum value for our area. So just plugging in to this formula, I'm going to move this over just a bit so I have enough room. So plugging in 600, if you throw this in a calculator, you should get 720,000 for the area, right? And so that means that our maximum area is going to be is 720,000, and since our fencing was measured in feet, that means we are measuring our length and width in feet as well, and so our area is going to be in square feet or feet squared, whichever way you want to write it. Okay, now if we want to actually truly answer this question, it does ask what are the dimensions of the field that has the largest area. So we have found the maximum area. The dimensions are just asking for the length and the width of the field. So we know that this max occurs when W is equal to 600. So let's see. So this occurs when W is equal to 600, and when W is equal to 600, we know that L from this formula will be equal to, let's see, if we plug in 600, we'll get 2400 minus 2 times 600, which would give us 1200. Okay, so our actual answer is going to be W equals 600 and L equals 1200 feet. Okay, so that is our first example, and then we will do some more in the next video.